I will again give that part. Okay, so I'm just going to share my screen. Okay, so this Amazon Redshift is basically a data warehousing service on AWS cloud. Okay, data warehousing service means this is going to store your data that is going to be utilized for your analytical processing. In most of the project, the data warehousing or data warehouses are the targets for your data pipelines. For example, AWS has Amazon Redshift, Azure has Synapse, Google has their BigQuery, and some third-party tools are also there, like Snowflake is there, and some other tools are there. The concept of data warehouse says you store a large amount of data, you run some queries, or maybe connect it with some dashboarding tools, or maybe connect it with some machine learning operations tools, and use this data for your analytical purpose. That means uh, we have our final data. Final data means the extract, transform, load. The final step is load, and that load actually happens in the Redshift on AWS cloud. So in by definition, Amazon Redshift is a fully managed. Fully managed stands for you no need to manage any system softwares, any securities, patches, OS upgrades, or installations, or all those things you have no need to manage. It is completely fully managed by AWS cloud. It can handle data up to petabyte of scale, and ideally you should start with gigabytes of data, and we can scale this data to petabyte later stage also. But it is not mandatory that we start from gigabytes, but for practice purpose we can start from KBs and MBs also. But it is advised by AWS that if we have gigabytes of data load, then only we should load Redshift. Otherwise, we can still use AWS Athena for the same task and purpose. Here, actually, as I mentioned, that we can store data, and using this data, like end customers can be different here. It could be that last thing, Redshift is of the end customer. Here I'm running some queries, and based on those queries, I'm generating some reports, and based on those reports, I am predicting the future of my organizations, and accordingly taking the decisions for its betterment. But obviously, we guys know that nowadays reporting is not happening on CSVs or Excels, or this reporting layers. That is kind of an older way of doing it. Now, very beautiful and very informative dashboards are built on the BI tools. Though that BI tool could be your Microsoft's Power BI, that could be Azure's, Amazon's QuickSight, that can be Tableau. So uh, those BI tools actually get the data from Redshift, or it could be some other data warehouse also. Or we could use this data for our machine learning algorithms, and we can feed this data into machine learning, and accordingly decide the future of our organizations, and that's how we can plan things. So this is the introduction of Redshift, and yes, the Redshift or warehouses are not similar as your databases. You should understand this part. Databases and data warehouses, they are similar, but they have completely different functionality. They are not, a database cannot replace data warehouse, or neither the data warehouse are built to replace databases. So we need to understand that part also. Databases are built for your OLTP transactions. Data warehouses are built for your OLAP transactions. So yes, if you have any questions in introduction part, let me know, please.
I one question. In database, suppose we are using SQL, and already in local system only the data is getting stored, and we are firing some query and getting the output. In case of data warehouse also, like Athena, we are firing a query, and as a backup we are storing S3 bucket, right? So the exact difference between database and warehouse, this I didn't understood.
Okay, so see, there are two kinds of applications these things are supporting. Okay, so for an example, the let's take a banking example. Okay, we all have the credit cards and debit cards. We may do various kind of transactions, maybe via ATM machines, maybe via some POS machines, maybe via online payments. Okay, and when we do a credit card transaction, that is a single transaction, and that single transaction's details, what time it was, how it was authenticated, what was the amount, from which account to deduct it, where to credit it, what card type it was, which ATM machine was used for that transactions. This is a single transaction detail, and these details gets stored on databases. Now, this process is actually called OLT. That means online transactions processing. That means you are processing millions of small transactions every day. And for this kind of transactions, databases are built and optimized. Okay, so behind the scenes, databases are your MySQL, your PostgreSQL. Amazon has Aurora also, your SQL Server. These are your databases. So their work is to store single row updates, deletes, inserts, or upserts. Okay, this is your databases. Now in data warehouses, so basically what the process that most of the project follows, like let's say that the same banking application, one day transactions are done, and maybe they'll decide some cutoff time. It could be 12 p.m. of night, it could be 10 p.m. or like anytime they will decide. And at that time, they will push the current day's transactions from databases to data warehouses. No, obviously not deleting it, just copying into data warehouses. So data warehouses are built for millions of rows in single transaction. Just understand this difference. Databases are built for single rows, but in million times. Okay, millions of single rows. But data warehouses are built for million rows in a single insert. Understand this difference. Databases are used for your storing the current state of your application. That means they will have the details about that how much balance you have in your account, what was the last transaction, who detected, like those transactions are going to be happen on the databases, and they are mostly going to have the live status of your database data. Okay, but data warehouses, they get the data from databases, and they get the complete data at once. It's a bulk insert or bulk copy, you can say. Once that data arrives on data warehouses, here we run the analytical purpose queries. The queries aim is to analyze your data. That means to understand which area, which city is bringing good business for you, where you are lagging, what could be the reason of your failure on that particular region, what are the pros and cons or limitations or insights like whatever you can get, that you get from the data warehouses. Like those systems are built for your analytical processing. That means OLAP, online analytical processing. And on the other side, databases are for transactional processing. So all the transactions, the complete days transactions, complete month transactions, your databases are directly connected with the outside world applications. And on the other hand, your data warehouses are connected with databases to pull the data or maybe push the data. But here we are not doing a single row updates, deletes, insert, and those kind of things. We are running bulk queries and we are just trying to get the information that how we can improve the organization's performance in the future. Okay, one more thing to remember, you can do this analytical queries on databases also. Okay, and you can do single row updates, deletes, and insert on data warehouses also. That is possible, but they are not optimized for these things. Okay, databases are not optimized for your analytical processing. Data warehouses are not optimized for your transactional processing. You need to understand this part.
Yeah, got it.
Okay, so now let's move ahead. Okay, so here what's happening here is, so in this blue box and this big blue box, we have our Redshift, and Redshift has two parts. Okay, majorly you can divide this Redshift in two parts. That is your Redshift storage and compute nodes. Basically, this compute nodes itself has the storage capacity, but you can divide this things in two parts. That means Redshift storage and Redshift compute. So storage is actually very much simple. It is just some GBs of storage every node you will get that you can use to store your data on cloud. And this data size is actually the compressed storage that I'm going to discuss. And then we have compute power. Okay, some compute power is always required to perform the queries that we fire. So basically, here we create a cluster, and cluster means multiple machines are going to be combined and treated as a single machine. And that thing is actually called a cluster in very easy language. That is a cluster. That means when one or more than one machines are available to perform same thing. That means when you can divide your work in parallel is called a cluster. So in the diagram that we have with us, we have a 4-node cluster. That means CN1, compute node 1, and compute node 2, compute node 3, compute node 4. We have 4-node cluster here. Okay, and then we have a leader node. Okay, so one of these, there will be a leader node, and there are 4 nodes you can say right now we have. The responsibilities of leader node is to connect with client or user. Okay, when it receives the some request, that means that when it receives the query, generate the query plan, uh, share that query plan with all the compute nodes, and inform them which data to be utilized for this query. Okay, once these compute node receive that information, and also the leader node actually divides the task. So let's say it identifies that 1 GB of data is going to be scanned by this query, then it's going to divide the task in 4 parts, and these 4 parts are going to work, or 4 nodes are going to work parallelly. Okay, so here these compute nodes are actually responsible for receiving the inputs. Inputs means the data and the query plan for and the amount, like which part they have to work from leader node. They will perform this task. Once their task or work is completed, they are going to respond back with the results to leader node. Once leader node receives the output from all the compute nodes, it is going to collect it and give it back to the user who submitted the query. So this is how a parallel processing happens in the Redshift cluster. Okay. Now here clusters are also actually this compute nodes are actually also divided into slices. That means the compute power that they have, it is again actually getting divided into multiples of slices. So you can understand it like this. Let's say we have a file on S3, and that is of a 10 GB of file. And we use a copy command to copy the file on Amazon's Redshift cluster. Okay, so if I do not divide that file, or if I do not, create some multiple pieces of that particular file, What is going to happen? Leader node is going to receive the request to copy that data into Redshift data storage and using these compute nodes. And as it has only one file, it cannot, it won't be able to create a parallel processing here. It is going to assign the task to one compute node, and one compute node is only be able to use its one of the slices that it has. So in this current diagram, let's say we have 4 nodes and we have 8 of the slices. So obviously, this is going to be wastage of resources. Like you had 8 slices, but you are only using the one of them. Okay, but if I break down that file in the multiples of 8, okay, I mean, you could break down that file into multiples of anything. You can create 20 pieces or 30 pieces or 10 pieces, like any number of multiples you can create for that particular file. But it is advised that you should, divide a file into multiples of your numbers of slices that you have available in your cluster. So that is the best case scenarios. So if I divide that file into multiples of 8, that means I could divide it into 8 parts, 16 parts, 24, or like that. In those cases, my all 8 slices are going to be work on that particular file to copy the data from S3 to Redshift, and it's obviously going to be a pure parallel processing, and that is how the task is going to be completed with very low response time. Okay, and here one drawback that I feel on Redshift is we have no choice of storing the data separately and compute power separately. Like when I'm going to create the cluster, I'm going to again explain you this, but this means, let's say I have a 160 GB of storage that I get on my smallest node, and let's say I need 10 more GB of storage, but that is not possible. I need to install one more node, and that is going to cost me double of the current price. And pricing wise, for a practice purpose, first 2 months of account creation, Redshift trial is there. But I will still recommend you for a better practice that once you launch a cluster and once your practice is done, please go ahead and pause that cluster. No need to keep it open. So yes, if you have any questions about this. Any questions? Varsha, Rama?
No questions.
Is it clear or it just completely went from top of your head?
Yeah, so I think we have to process the files through Glue, right, to Redshift.
Yes, actually we can do that also, but
And Lambda serverless.
no, Lambda, I mean, you can do actually,
Okay.
but basically it is the copy command that we use behind the scenes, and it is not advised to do row level updates on Redshift. That's why it is advised that you create a first, once you process the glue job, and it is advised to create a Parquet file and store it on S3, then fire up a copy command to copy the data into Redshift.
Okay, got it, got it. Yeah. Okay, curated folders. We have to put the curated folder, all the after all transformations. Then from there, from data lake to Redshift, we have to move the files, right?
Yes, kind of. Because if we directly try, first of all, I don't think that without any third-party software it's possible. I have actually I just tried that a few months back. Some connectors, third-party connectors were available, but not natively by AWS. And secondly, that technique actually will have the drawbacks because when you connect with database data warehouse directly, it's not going to do bulk insert for you. It's just going to do line by line copy into your data warehouses. That is not actually advised in data warehouses. Data warehouses says you copy the data in a one copy command. Just try to copy most of your data in single copy command.
Okay. Okay. But even though we are going to do one demo, the transferring files, the S3 to data, I mean Redshift, right?
Yes, that for sure we are going to do.
Okay. Thank you.
Okay, so this is how it is, and you can see that this is just a part of the same Redshift cluster that manage storage and the compute nodes. Basically, the compute node has the storage capacity also. It is not separated from the compute node. Just for the easy understanding purpose, AWS has presented this diagram, and then we can have it connected with some databases and SageMaker. That SageMaker is a machine learning processing application in the cloud. Okay, and the files that we can input and output to from S3 to Redshift, we can have CSVs, JSONs, Parquet, and ORCs and Avros, and obviously most supported and most preferred or default format you can say is a Parquet file formats. Okay, what I have in the chat box.
No question.
Okay, not sure. Okay, then the process features, you can see massive parallel processing. So when I say that I'm processing using 8 slices for a single file, this is what Redshift means, the massively parallel processing. That means we can process data in very much parallel way. This is the feature of Redshift that we can process data very much parallelly. Columnar data storage, let me just open a file to explain that. Okay, so your normal databases, that means your MySQL, Oracle, or those things, they actually store your data in a columnar, in a row-based format. That means they store this complete row. Okay, this means all these 3 columns they are going to store row-wise, right? Like this is the one row, and then they will create one index on this, and then the next row, and then they will create an index of this row. So like this, we store data in a OLTP based databases, but in data warehouses, be it any data warehouse, or I should say 90% of the data warehouse, because it might someone is doing differently, but I'm quite sure that Synapse, BigQuery, and these all things are storing in columnar format. So what is columnar format is, as it is known, when I say it is more optimized for analytical processing, as it is known that we are going to store this, or we are going to use this data that we are storing in the warehouses for our analytical purpose of queries. That means we might be having some columns where we are going to do more of joins, more of filters, or more of group bys. So that's why these warehouses try to store the data in a columnar based format. That means, let's say I am doing a filter. Okay, I am doing a filter and I am saying give me the row where listing ID is equals to 8110, the one that I have marked in red. So what row based data base is going to do for you? They are going to read this complete row. Okay, this complete row they are going to read row by row, and then they are going to find the amount, like where it is exactly 8110. So like this, they are going to read this data in a sequential way and in a row based format, and they are going to read the complete data. What is going to here, because as it is storing the data in a columnar based storage, it's going the column by column is storing the behind the scenes, and it also has the information about this other columns of the same row. So what it's going to do, it's going to read only this column. It is only going to read these listing IDs line by line. Okay, and then when it finds 8110, then only it's going to get this line. Okay, so basically if I just paste it here, then I paste this here, and then I can take it like this. Okay, so with the row-based systems, you are going to scan this much of a result for a filter query, and with the column-based approach, we are going to scan this much of data only. So you can see there is a huge difference. Like for the small data sets, we can see quite a visible difference, but we have more columns and more data. So these things does matter. So that's why these columnar-based warehouses performs better in your analytical processing. Okay, and then we have data compression. This means when data is getting stored on your warehouses on the Redshift managed storage, the data is actually getting compressed. It is, or let's say you have 100 GB of CSV file or a Parquet file. When you actually store the data, it is going to take around of 30 GB or 40 GB only. That means almost 60 to 70% of reduction you can see in the storage side when you store the same data on cloud on Redshift managed storage. And your queries are also actually executed on the compressed data. Once the query is completed and it little node identifies the results, only in that case decompression happens and you can see the complete visible data there. Okay, and then we have result caching. So more frequently our rain queries are actually those results are actually stored, and that we can actually go and next time if we run the same query, it is not going to read and scan the complete tables and databases. It's just going to get the result to us from that cached data. So that means Redshift can have the result caching also available with us. So yes, if you have any questions. Okay. Then we have distribution styles in Redshift. So again, coming back to this image, when I store my data in the form of tables or in the form of databases on this cluster node, or you can say Redshift, this data gets divided between these cluster nodes. Let's say I am storing some data, so it's going to get distributed between all these 4 compute nodes. Now, what are the logics and ways of distributing this data? That is called as a distribution style. So in Redshift, we actually have 3 distribution styles. And you can say this understanding the distribution style is a mandatory thing for when you want to say Redshift, because this is a very much basic building block of your Redshift optimizations. So we have 3 of those. So first is even distribution. That means let's say if I have 100 GB of data, so every compute node is going to get 25 GB of data and it's going to be distributed randomly. That means every node will have same amount of data and it's going to get distributed randomly. No logics and no algorithms is going to be utilized for that. Then I have key distribution style. That means when I have some column in my data on which I might want to do the distribution of that. So maybe if I refer some other data set. So let's say I have this data and you can see I have one column that is my sub region ID, or you can say region ID I have. So if I select this column for my data distribution, you can say I have total of 5 region IDs. And if I say distribute my data based on the region ID, then Redshift is going to select the region ID of 10. I'm just giving you an example. Okay. And you see all this data where the subregion ID is 10 is going to be stored on one of the nodes that we have in our Redshift cluster. Same way, the other region IDs is going to get stored. The other region ID, or let's say 20, is going to get stored on different compute node, and likewise the process is going to happen. So let's say we have more than, let's say we have some data and we say that my distribution key is subregion ID in that origin ID. So the particular region ID's data is completely going to be on a single node. This is possible that this compute node 1 can have multiple region ID's data. That means it might have region ID 10, 20, 30, and 40 also. This means, let's say, as you can see, I have just 4 compute nodes, but I could have more than 1 or more than 4 or beyond that also the region IDs. Okay. In that case, what will going to happen? One compute node might have more than one distribution key available, but it will not be possible that your key is present on more than one compute node. That means region ID 10's data, for example, can only be present on one of these nodes. It cannot be that it's present on compute node 4 also and compute node 1 also. Okay. So this is your key distribution style, where you choose a key in your data set for your table, and you say distribute my table's data based on this particular key, and accordingly it's going to be distributed on all the compute nodes that we have present in our cluster. Now, what is the benefit and disadvantages of the even and key distribution? So when I have some data with me that I know in future I'm going to use these particular queries, that means I can predict this, that in my future queries that I'm going to write, my particular columns are going to be used very heavily in the group by, in the joins, in the filters. In those cases, you might go ahead and select the key distribution style. Okay, and when your table is too large, also in those cases also you might just go ahead and choose the key distribution style and distribute your data based on some key column. Okay, so for this data set that I have available right now, ideal distribution ID is going to be subregion ID, not region ID, because it is also said that you should have high cardinality. That means that it should not be like that you only have 2 or 3 examples of that key. That means right now we have 5 separate keys here for this data set, and if I go on subregion ID label, then okay, it's actually 4 only, but if I have, let's say, more region IDs available, let's say 10 or 12 or 15 categories, in those cases, like hard card, okay, column that we choose for our distribution style, okay, it should be high cardinality, and it also should make sure that the data is actually getting divided into compute nodes at least or approximate evenly. This means it should not happen, for an example, that let's say I have India's data, maybe some GST data, or let's say maybe some Aadhaar card data, and I choose city name as a distribution key for my data. Okay, in that case, what's going to happen? So obviously the cities like Mumbai, Bangalore, Delhi, these cities are having very huge population. So obviously for these cities, data is going to be very huge. So what is going to happen? Your compute node is going to be completely filled with its capacity. Okay. And let's say I have some other cities data, let's say some tier 2 or tier 3 cities data, and that is placed on compute node 2 by Redshift. In that case, my compute node is completely exhausted with one city's data, and my compute node 2 is having its complete capacity free because it has almost nil data there. So we should also take care of this thing, like our key should divide data equally on all the compute nodes, and our key should be used in joins, group bys, and where conditions like those. And then that is the perfect example of our distribution key. And when we have no idea about this thing, like when we have no idea about our data, our future queries, or how we are going to write the queries, or which column is going to be dominating in our SQL queries, or like which column is going to give us the best distribution part. If we have no idea about these things, and if we have a large tables, in those cases we should go for even. So pros and cons, you can say. In even you have to do no analysis, and in a key distribution style we have to do some quite a huge analysis part there. And what I was saying, yes, yeah, even we have to do no analysis in key distribution style. We might have to do analysis, but if we can do that analysis and if we can get the correct distribution key, obviously in future we are going to get benefited by that, and our queries are going to take a quite bit less time, and its response time is going to be quite a lower side. So is it okay? Let me know if you have any questions about this key distribution and the even distribution.
So Redshift is a warehouse, and it will be using some storage like S3 in real time, and it will be parallel, and the data set what we had once we are creating a table. So we have to define the key also, and that based on the key only the data will be getting distributed among the Redshift cluster, right?
Okay, one thing is wrong here. Data is not stored on S3 Redshift. Data is stored on its compute node. Compute nodes have the storage capacity also. From S3, we can copy the data into Redshift, or from Redshift to S3, we can copy that data.
Okay, so Redshift also, okay, so for Redshift, it's a different separate server itself where it will play like master slave architecture, and in the slave multiple nodes will be there where the data will be getting copied in distributed way with the help of keys.
Yes, and keys also, if we can predict the future queries, and if you know this is the column that you can use as a distribution key, and it's going to benefit you, only in that case we choose the distribution style as key. Otherwise, even is fine. Okay, and then we have, yes, please, if you have any more questions.
No question.
Then we have all distribution. In this, what happens? So for the smaller tables, okay, for the smaller tables which are dominantly used in joins, it is advised by Redshift to copy the table on all of the nodes using all distribution. That means that table is going to get 4 copies in this case if we have 4 compute nodes, and it's all the 4 copies, like 1 copy each, it's going to store on this compute nodes. So in this way, what's going to happen when I write some join, okay, when I write some join and I am using a table that is distributed based on key, and then I have a table that is distributed based on all distribution. So in this compute node 1, I already have the all distributed table. Okay, let me just take this, take it like this. So I have a big large table, okay, and this is a key, and on the right hand side I have a all distribution table, okay, and this is distributed on all the nodes. So when I do a join between these two tables, and let's say I do join based on the distribution key, maybe on city, or like it could be any key. So for that key to join data with this table, it no need to go and check the data on all the nodes. Okay, for that particular key, no need to go and check the data on all the nodes. We can very simply it's not it's actually Redshift is simply going to stay on the same node, and it's just going to do that join. And in this process, what is the benefiting us? We have like Redshift is not going to shuffle any data. It no need to read the other part of the nodes, and it's no need to shuffle the data. So this is how the all distribution you can utilize in your architecture, in your Redshift. So when we have small dimension tables, if you understand the dimension and facts, when we have small dimension tables, those dimension tables we can go ahead and store with the all distribution style. So you got this part, or it's it's a little bit tricky. Let me know if you haven't got this.
Basically, smaller table we are storing as a all distribution table, so the data should not be suffered. But in case of big large table, we are storing as a distributed by key. But in this case, data will shuffle.
Yes. Not in the case that data will shuffle. Let's say you do a group by, or let's say you do a join. So all the Mumbai's data, let's say I just take Mumbai. Okay, I see the example of Mumbai, and I have the Mumbai's data on compute node 1. Okay, then on compute node 1, on my dimension table, I have Mumbai data, I have Bangalore data, I have other cities data, let's say Delhi and some other cities that I have. So to like this is also on compute node 1 because it's just distributed on key, and this is all distribution, and it is available on compute node 1. So in the joining process, it's going to see Mumbai, and it no need to shuffle data between other nodes. Okay, this is one thing. Let's say on compute node 2, I have Delhi's data here. Okay, and I have something like this. And again, same thing, because it is because it is all distribution, same thing is available on compute node 2. So Delhi is going to match with Delhi. Okay, and no need to shuffle data. But let's say this is not all distribution. So if I just remove this, okay, let's say this is compute node 1, compute node 2, and this compute node is having Delhi. Okay, it is having Delhi, and let's say compute node 2 is not having Delhi. This is I'm saying about even distribution, because it is random. Anything could happen here. Or it could be possible that some of the Delhi data is here and some of the Delhi data is here. Okay, so in this case, if you want to join Mumbai, okay, obviously compute node 1 does not have that data, and it's going to see also that my table that I'm going to join with, it's not even, it's an event based distribution. It is not a all or key based distribution. So by default, actually, it will look for the join on all the nodes, and it will require to shuffle the data. You got this point?
Yeah, so in this event distribution, so CN1 has Mumbai data, and in case of H column, in CN2 there is a small data is there. So in this case, the data would shuffle, but which table would shuffle, that also we can control.
No, it's actually not control, like this shuffling and all this moving is not done by actually us. It is Redshift is actually behind the scenes taking care of that. But if there are more options to perform a join, obviously your queries are going to take more time. So that's why we should optimize our queries using the distribution styles. And what do you ask?
Uh, my ask was like which table it will shuffle. That I got, like it's depend upon Redshift only.
Yeah, it's actually a smaller table. It will shuffle. Thus, it will intelligently try to shuffle the small amount of data only.
Okay. Any specific size?
No, not size. If it will compare which table is bigger one.
Okay.
obviously see, and this table is right table is a smaller one, so it's going to shuffle this table only. Okay, I mean, if you have questions, you can ask me because right now I'm not feeling too good, and I'm going to continue some other parts of Redshift, like some short keys and Redshift spectrum, and then we have one more part of Redshift to cover. And obviously, we have to launch the clusters and connect the clusters and write some queries, load the data, unload the data. So those things we are going to do.
Okay. I have one more question. Athena is like serverless, but we cannot make provisioned in our AWS. It's just one option. It's serverless only. But in case of Redshift, we have both the options. Like we can make it as a serverless also and provisioned also, and we can use it.
Yes, actually, a few months back they have introduced Redshift serverless also.
Okay. No question as of now from my side.
Okay. So okay, guys, I'll just stop recording.